Okay, so what we're going to do this morning is talk, for this lecture at least, about a little about STL, Standard Template Library Containers. But first I want to go back to, briefly, to a topic we've raised before and you've seen before, which is overloading of function and operator names. So even in historically conventional programming languages like C and Fortran, we do overloading. That is, plus, star, minus, slash for arithmetic operations are used with many different kinds of arguments and different meanings in different contexts. So it's in A times B is understood as multiplication of A and B for integers and floats. The fact that you can use a function name for different kinds of arguments is what's called overloading. We overload that function name to mean different things in different contexts. C++ takes this to the limit consistent with static strong typing. So, so operators like, that should be a plus, not an X, plus, star, binary infix operators, and prefix, postfix operators, plus, plus, minus, minus, are all can be defined for arbitrary sets of types, provided it's unambiguous with respect to those definitions. Now, there is a funny business that occasionally you get burned by, is that operator precedence is not something you can change. What does that mean? It means if you have an expression with multiple operators, with plus, times, whatever, divide, the order in which there's an implied set of ways of putting parentheses around those things that makes expressions involving operators unambiguous. That is what's called operator precedence, and that is something that is tied to the operator independent of the context. You can't change that. So I'll give you an example, is that in at least some symbolic manipulation packages, such as Mathematica and Maxima, hat is used for exponentiation. And it actually binds more tightly. Hats are evaluated first before multiplication. However, hat has a lower precedence in C++. And despite the fact that you may want to use it as something that has a higher binding, you can't. And I tried doing that once, and it was very annoying. So that's something you can't control. But other than that, you can use operators any way you want. Function names can also be overloaded. So I'll see, you've seen examples, and I'll show you a few more to clarify things in a minute. And everything is uniquely determined by types of arguments, return values, and membership as function members in a class. You can also get one more level of overloading by using namespaces. If, for example, we had our own vector and wanted to use both that vector and an STL vector, we could do it by means of, first of all, saying don't use default using namespace std, and then have a prefix std : vector. So as we're not really using namespaces in this class in that formal a way, because we're not building anything quite large enough for that to be a problem. So here's some examples of overloading. So one that you see all the time, even though you may not realize it, is the stream operator. Greater than, that operator is an operator. It's one of the list of things that are defined as binary infix operators. That is, it takes an argument on both sides. And the operator takes, in general, the way it is used is that we have two arguments. The left argument is a stream, and the right argument is something, is another type, and these are templated. And the syntax is if we have a stream such as Cout, which is the stream to standard output, terminal output, greater than t, well, what that does is that sends the value of t into the stream Cout. And you have to have defined what that means. And it typically means applying another stream to the member data of Cout of t until you finally get down to plain old data, primitive object data where those things are defined. So you can build up lots and lots of stream output operators, and they're all overloaded on the type of what you're feeding to them, and you can write them yourself. So that's an example of overloading you will use a lot because you want to use stream output is a very convenient notation to use. Here's another example of a more conventional form of overloading. I didn't do in the in your first homework assignment anything about more elaborate forms of operations on structured grids, on rectangular arrays. However, later when you do the kind of performance programming assignment, what I may do is let you have a library that has lots of these things and has them implemented in a way that is quite fast. So here's an example of a kind of overloading you would do. So we have a rectMD array of Tn, so the values have type T and they're n components. And you have an operator star equal. Now, what does star equal mean if what you're star equaling is a member of is an object of type T? Well, it means I'll tell you what it means in the case of rectMD array is that you will star equal each element. It assumes that there's a star equal defined on pairs of type T. And you will star equal each element of the type. So what is this meaning? This is saying do scalar multiplication by something of type T. On the other hand, there's another form of multiplication that's quite convenient to have on rectangular arrays, which is you take two rectangular arrays and you multiply them component-wise to update the first one with the product of each rectangular of the value of each rectangular array. So you take the two rectangular arrays, and you for each element in the array you replace it by the product of the elements in the first and second array. So that's a perfectly good star equal that you can define. It's the same name. How is it disambiguated? Because the arguments it takes are different. In this case, we take we take an array as the second argument. Here we take a value type T. So let's see. Another example of overloading, again, we've already discussed this, is indexing. The indexing operator on rectMD array takes two values, a point and an int. So it takes a grid point at which you're evaluating, and it takes the component number. Now, the first line and the second line are two different types. Why? Because they have different const behavior. This is returning a const reference, so it's saying, give me that reference, and it's guaranteeing that nothing is going to get changed in the array by applying this function. Here we have a non-const version of that. It returns a non-const reference, even though the arguments are the same. Putting in the consts where we're putting them in changes the type. Now, so that can be disambiguated by the compiler and say, oh, those are really two different functions. And why do we do this? Why do we have two different types? Because in the case where we're indexing into array to construct a right-hand side, we're not modifying the array. We're just getting the values and computing something. In the case where we're indexing the array to provide a left-hand side and to store something in it, that's different. And one of them can be done with non-const, one of them has to be done, one of them can be done with either const or non-const, but the indexing for a left-hand side must be done with a non-const version of indexing. Finally, there are member function names, and I've mostly been looking at operators here, but we see lots of examples of that. And in STL containers, you will see lots of examples of the same names being used for member functions, and deliberately, because you want to use the same name as a kind of documentation and mnemonic for member functions that have analogous functionality across on different container classes. So for example, when we talk about iterators, the syntax for iterators, the names that we have for the various things that iterators do, will be the same for all the STLs that have that particular kind of functionality. And that's a good thing because it's unambiguous, because you know the classes are different. And it gives you a standard way when you're reading the code saying, oh, this is standard iterator syntax, I know what it's doing. So, so moving on now, let's talk about standard template library containers. So these are predefined classes, aggregates that are templated over the type being held. We have these live in the std namespace if we needed to disambiguate it, and we're using namespace std to use that as the default place you look for things. This is all C++ 11 stuff, the way we are doing things in this class. C++ 11 is now sufficiently stable, so that I'm feel comfortable with standardizing it on it in this course. So what are the various container classes that we have? We have C arrays as first class objects. We've already seen that. Dynamic arrays, which are vectors. Various other containers, queues and stacks, priority queues. We won't talk about those. The two others we will talk about are linked lists, which is the list class, and associative arrays, which is the map class. Oh, by the way, for those of you who are actually listening to this lecture in real time, both of you, the lectures are posted in the resources site, so if you want to download them, you can get them and take notes. These things are different containers that are distinguished by the kinds of access they provide and the complexity of their operations. To use these, you're going to have to include the appropriate header files. So, for example, include angle bracket array angle bracket. That's looking for a system header file, C++ system header file. So here's the first two that we've already dealt with. Array tn and pair t1 to t array we have dealt with, pair we'll be using. So these are kind of little things, but very useful. So why not use int of something, 3 or n, where n is a compile time constant provided to you by the by preprocessing, rather than an array of int 3. So array of int 3 is a type. Objects of this type can be returned or assigned. And it's the return thing that is really annoying, that that really makes this a useful thing to have. So if, for example, we have a function here, something we'll call tuple function, that takes some arguments and returns an array of ints of 3 ints. This is a perfectly okay function signature. Return value is a class, and it takes arguments, and off we go. On the other hand, if you tried to feed this second line to a compiler, it would say it doesn't make sense. This syntax is illegal, and there's really no way to get this effect. So one of the things that by embracing array fully, you'll see later in the next lecture when we talk about unstructured grids and finite elements, there were a bunch of places I was going through the lecture this morning, and there were a bunch of places from the last time I taught this class where I had to use as return values vectors. And vectors were the wrong answer. What I really wanted was an array of 3 components. And now I'm embracing arrays fully, and I went back and I'm changing all of those vector return values to arrays because it's a class. It's a legitimate return value. Now, pair is another thing that comes up as kind of a useful helper in lots of different ways, in a way that you define things on the fly. There are lots of circumstances under which you need to hand around pairs of objects of different classes. And we'll see some in some of the one of the container classes. So there's this thing called pair, and pair of T1 and T2. It's templated by the 2 types of the 2 things that you can make. And here's a typical function that returns pairs, make underscore pair T1 and T2. And in fact, you can use this as a kind of, there are lots of flexible ways that when you look at examples, you can see how this can be used. How do you get access to what's in the pair? Well, pair has a member data first and a member data second. So that's how you find out where things are, find out what's in the pair. But it gives you, as I said, it's a handy thing to have, particularly when what you need to do is return 2 things rather than 1 thing. So we've talked about vector before, so let me give you a snippet of vector code. So we have a vector of int, foo, and what I'm going to do is I'm showing you a piece of code that builds the vector and then outputs the vector to standard out. So here's it. This is not meant to be understandable. It is meant to start a discussion. So we loop from k equals 0 to n. What I'm going to do is fill up vector with the values 0 to 9. And the way I do it is calling a function called pushback. What's that? And then what I'm going to do is iterate through all the elements in vector, and on each line output the value. And there's a whole bunch of syntax here that just looks like gibberish. So what we're going to do is unpack that syntax, because there's lots of good stuff there, and it's not just about vector, it's about the other good stuff. So there's several new things here. First of all, here's a comment about classes declared inside of classes. What can be declared inside of a class A? Well, you can declare functions. We've already seen that, a : bar. You have data members, a dot m sub foo. That's a data member that you have for 1 per object. So I'm writing down how you access these things. Now, if for static members, where you only have 1 per class, the way you access them is the same way you access functions. In some sense, you only have 1 function per class. You don't replicate the function itself. You may use it on different values, but you don't replicate the function itself for every instance, for every object. So this has the same character. Static members, there's only 1 s underscore bar per big A, and you access it by a : s underscore bar. Turns out there's a third thing that you can define inside of a class, which is another class. So you have a : a prime is some other class. The example of this is iterator, and this is a repeated idiom in container classes. Vector angle bracket t angle bracket : iterator is a class member of vector t. It abstracts the idea of a location in a linearly ordered set. So iterator equals vec.begin, so we have something that's of class vec. It calls a member function of vector of t that returns an object of class iterator, vector of t iterator, initialized to the initial location in vec. So second thing is iterator.it.end is equal is something that returns a Boolean. It's true if you've reached the end of the vector, and it's false if not. You can increment your iterator, plus, plus, minus, minus. You can increment or decrement, plus or minus direction. Star it returns a reference to the contents of the current location in vec. So iterator is something, when you define it up here, it is an iterator associated specifically with this vector. So that means when you are evaluating star int, it is taking current location, returning a value. That's the value in that current location in vec. Now, you could have gotten the same functionality by an ordinary loop and indexing, but only for vector, not for other containers. In addition, there's something that this iterator doesn't allow you to do that the indexing notation does. Let's say you have two vectors and you want to take a dot product of them. Well, the only way you can do that is by saying, what is the relationship between a vector at with the value at one location for one vector and the value at the same location for the other. The only absolute notion of location you have that transfers between both vectors is the index k, an integer index. So iterators will not do everything, but they're a repeated idiom and they do lots of things for you. Now finally, let's go back here. For auto, what that looks like a type declaration, but what's going on there? So this is another C++ 11ism. Oh, don't, please say this isn't happening. All right. 4 squared. I'm going to have to just go to the PDFs because, all right, this is 7. L. So auto. So if I wanted to have an iterator loop, and this is any sort of iterator loop, it's, what's your starting condition, what's your termination condition, and what do you do each time through the loop to increment things. Well, what I should have typed was vector t : iterator it as the as a declaration of what it is, what it is, and then equal to vec.begin. That's a lot of keystrokes. What auto does, and it's something that's more generally useful than just in the beginnings of loops, is auto variable name equals ... can be used instead of a type declaration if the type can be inferred unambiguously from the right-hand side at compile time. So I could replace, in this particular case, what I was doing was replacing all of these keystrokes with auto. And why could I do that? In this case, vector of t begin has not been overloaded. There's only one member function with that name and no arguments, and its return type is vector of t : iterator. So because the right-hand side has an unambiguous return type, then we can use auto instead of all this other stuff. Obviously, auto can be used for many other things besides initializing iterators. As a matter of advice for readability and self-documentation, it's probably best not to overuse it. And one of the warnings is compilers can find meaningful interpretations of what may be typographical errors. So, however, in this particular case, it's pretty safe to use it. Why? Because as you will see, this is where overloading versus non-overloading in different ways is helping us. Vec.begin, anything .begin, a container class .begin is a standard notation in container classes for return an iterator and set it to the starting point. So when you look at this, it's going to be completely unambiguous to your eye, not just to the compiler, what it is you're doing. And so auto is safe to use here, and probably even a good idea. Now, let's talk about how you add, delete, access elements of vector. Here's a function that you have. How big is your vector? How many elements do you have in it? Here are two functions, pushback of t and popback of t. What pushback does is it says, okay, I have a vector. It's of length whatever, and what I'm going to do is add to the back of it, at the very end, add one more element to the vector and set that value to t. Popback does the other direction. It says go to the very end and delete the last element of the vector. Back and front tell you how to get access to the first or last elements of the vector. And in fact, in vectors, we can index by integers. They are really contiguous. They really have a syntax that at least that looks like contiguous array. This really looks like a 1D array. You can index any element by an integer less than size. You can add and delete elements at the end of an array. That's what these two functions do. And you really are getting fast access. Remember when we talked about locality in space, locality in time, caching? The fact that you are that the part of what is the definition in the specification for vector is that the data is stored in a contiguous block. That is, as if it had been allocated with new. So it's a large chunk of data. What that says is that as you walk through the data one by one, you are accessing adjacent locations in memory. That's a good thing from the point of view of getting cache reuse and other things that improve performance on systems. In fact, you could access the underlying contiguous storage as if it were an ordinary 1D array. You could grab the location of the front, take its address, treat it as if it were an array. So let's go back to vector of t and our little loop, and now we can understand what's going on here. We declare vector foo to be a vector of ints, and initially foo is empty. It has no elements. So now for int k equals 0, k less than 10, k plus plus, we add to the back end of foo a new element to the array whose value is k. So it's going to be 0, 1, 2. So the array will end up being 0 through 9, and it'll be of length 10. What this line does, auto, it is inferring an iterator here, foo begin, foo not equal to end, increment the iterator, and what am I doing? I'm saying send to cout the value contained at the current location of the iterator, and then a new line. So what this will do is print out, one on each line, 0 through 9. Very easy. Everything just works. Now, what things do vectors not do well? How do you remove an element from a vector? Well, it's easy to remove an element at the end, but in general, the only thing you could do is find the element you want to remove, make a whole new vector, one smaller than the original, and copy all but the excluded object into the new vector. Horrible, very expensive. So we've already been doing something that on the face of it would be almost as awful with pushback. Pushback says grow the vector length by 1, copy all the elements into the new vector with length 1 larger, copy the new element at the end. Well, in fact, that's not how vectors work. Vectors work, what they do is they, let's say you start out with some vector of length p. It actually has allocated more storage than that. And so even though you don't have access to it, you don't use it, it's there. So if you do pushback, okay, I actually have the storage, it's contiguous, until I get to a limit. There's an initial length I've allocated. What am I going to do when I hit that length? What's pushback going to do? Well, pushback's going to create a new array. Think of it as being double the size of the original one. And now that gives it a lot of headroom for adding new things in. So you always have contiguous storage. The location of that storage may change from pushback to pushback because it gets bigger. And what's the cost of having this flexibility? Well, it says, in some sense, you have to double the storage that you would otherwise need for the vector. And every so often, you have to compute a new vector and copy. And every so often is kind of log in the size. Number of times you do it is log in the size of the vector. That's kind of the good way of doing it. So that says this is actually pretty efficient. And there are things that it's really good at. Accessing individual elements by their position index. You can index by k, and that takes constant time. It takes no time at all, practically. You can iterate over the elements in any order. You can do random access. You can say, okay, k equal to, I can do, some random sort of integers and index into the array in any order. And it takes me as long as I have as the number of integers. Now, adding and removing elements at the end, here's a piece of terminology that's interesting. It's constant time. It's not constant time because anytime you have to grow it, that's a big cost, relative to just adding an element. But it's constant amortized time in the sense that if you average the time that it takes to do that, to grow it and do that additional copy, over all the times you've added elements, the cost on average is the cost of doing that copy is amortized over all of those additions. So, and it's a constant cost per addition. So that's vectors. But remember, there are things that vector is not good at. We still don't have a good way of inserting and deleting at arbitrary locations in a vector. So to fix that, we go to another container, list. List provides the following features. It's efficient insertion and removal of elements anywhere in the container, and that's a constant time cost. Efficient moving of elements and blocks of elements within a container or even between different containers. Iterating over the elements in forward and reversed orders. Lists are ordered as the common, in much the same way as the common usage of the term is. There's an order to a list. So here's a little schematic of what a list looks like. An element of a list is going to be something that contains whatever your value type is, or object of your value type is. So in this case, here's a list of integers, 12, 99, 37, whatever. But it contains two other things. Each element of the list contains two other things in its internal representation. One is it contains, so let's look at 99, it contains a pointer, a way of accessing the location just in back of it, and a way of accessing the location just ahead of it. So if what you want to do is walk through a list, the one thing you have to add to it, whether you're walking forward and backward, is what is the location of the start and what is the location at the end. If you know that, then I can start from here, walk, increment here, and all these things are fast to do. What this is not good at is random access. With a vector, I can go to element 35, and that's very fast. To get to element 35 in a list, you have to start at the beginning and walk down the linked list to element 35 and return it. So here's some highlight functions. By the way, the standard website references for C++ will have this and much more. So here's some highlight functions. You can ask what its size is. You can do pushback and pop back. And in fact, you can do it on the front as well. So you can add a list to the end. You can add an element to the list at the end. You can delete one from the end. You can add one to the front, delete one from the front. You can find out where you can find out what's in the first and the last elements of the list. Now, you can insert. Now, what insert does is it takes as one of its arguments an iterator. and the other argument is a value. And then erase takes an argument that's an iterator. And then you have the list usual iterator. I'm sorry, this is wrong. That syntax is just gibberish. It's list of t : iterator gets you begin just as it did with vector. It's same syntax. So what is this telling us? What does this mean? In order to insert something, you have to know a location, and that location is going to be given to you by an iterator. So here's the picture of how you would use list. You're walking through the list. You have a condition for where you might want to insert something or where you might want to delete something. That's based on either absolute location or the value inside the list. So you say, okay, I've reached a certain point here. I want to insert something here. You have a value for the iterator that allows you to insert. You have a value for the iterator that allows you to erase. You can also do this with chunks of data. You can erase, insert, and delete chunks as well as just single elements. Notice there is no indexing operator, no square bracket. But insertion and deletion is cheap once you're at the location that you want to insert and delete. So why use list? Erase, insert, splice, and merge, which are kind of more aggregate operations, are order 1 complexity. They're remove and unique are things that are order linear complexity. So removing something, so these are different forms of doing things that are more aggregate operations. So one thing that happens with lists is that they also do a lot less copying. So if copying is expensive and you are doing things that are quite dynamic, these are better things to look at. So that's lists. Finally, the third container that you use a lot that's extraordinarily useful is map. It's an associative container. It's templated on the type that's being stored, but it's templated on two things. It actually, let me go forward. So map is templated on the type that you're storing and a second type, key. So it stores elements formed by a combination of a key value and a map value. So why would you want to index by anything other than integers, for example? So think of this as vector, where the universe of indices are some arbitrary type. Well, dictionaries are examples of maps. You have what you are storing is a definition. What your key is, what you index by, is the word, is the string that defines the word. You index into a map with the key, and you get back out the value. And as I said, you could consider a vector a simple map where the key is an unsigned integer and the value is the template class. But that would imply a constraint that the keys are in the continuous interval 0 to size -1. What if your keys are not that simple? So this is a way of handling that. As I said, map takes two template arguments, one for the key, one for the value. Now, for maps, for this particular class, maps not only give you a way of storing things of constructing dictionaries, but they also give you something else that's nice to have with dictionaries, which is dictionaries typically are in alphabetical order or some ordering. So if you have map requires the key to implement the greater than operator. And the properties that the greater than operator has to have is strict weak ordering. That is, if A is less than B and B is less than C, then A must be less than C. So if these are all key elements. If A is less than B, then not B less than A. If not A less than B and not B less than A, then A and B are equal. So these are reasonable things for strict ordering. There is one other thing about this, is that you only have one element per key, so per key value. There's another class, which we won't talk about today, which is multi-map, that allows you to have multiple things per key value. So here are kind of some of the highlight functions for map, where its template types are T and key. Again, you can ask, how big is it? What's my current size? You can insert a pair, T and key, and a key. You can change the value at a current location in an iterator. You can erase a value at a current location in an iterator. You can also erase a value corresponding to a particular value of the key. And that ampersand should be on the other side. You can get to the front, get to the back. Keys have iterators. I don't know where my brain was when I was typing this last night, but I have this consistent error. I will fix that and push a new version out. We have an indexing operator, and it's just like the int indexing operator, except you index with a key value. So there's a simple dictionary object that I will just skip here, and I have a better example that's more attuned to scientific applications that I'll do here at the very end. So there's another version of map, which is unordered map. It has the same interface as map, but it doesn't have any ordering. Key does not have to have the key type does not have to have greater than on it, but it uses a different mechanism for inserting and deleting and keeping track. It uses a hash table for this. It's optimized for fast lookup. Map is order log n insertion and lookup. Standard unordered map is order log n insertion and order 1 lookup. So it's very fast to look up things in a map, in an unordered map. It has a more elaborate way of doing faster lookups. It kind of combines this with binning. You'll see an example of binning in the next slide. And it relies on the concept of hashing. It turns a key type into an integer in a way that has few, if any, collisions. So if you have a key type, strings, whatever, you have a hash function that turns that into an integer, and then what it's going to do is index into an array of linked lists, into a vector of linked lists. So few collisions say that when you index into this, you will mostly get a unique value. Occasionally you'll get more than one. Well, if the hash function is a good hash function, by which we'll leave, this is the definition of it, the number of collisions, the number of redundant locations into this hash function will be small. You may get 1 or 2 or 3, but not a pileup of order n collisions. It's not a particularly good choice if your access pattern is visiting every member, but it's really great for doing, as I said, for doing lots and lots of lookups. So now the last thing I'm going to do is show you a little example of how you use a map to do something that happens a lot in modern kind of scientific applications. So the idea is this, that this is kind of a hierarchical use of rectMD array. So what you have, let's say you have partitioned space into a uniform grid. So that uniform grid is actually representing a region in space. And now you have other things in that uniform grid. An easy example is particles. So you have a bunch of particles in a uniform grid. And one thing you know that you often do with particles is that it matters when you're computing force fields or other things, it matters which things are near to you and which things are far away. And having to kind of walk through all the particles to find out who your neighbors are is expensive. So what we do here is something called bin sorting, which is to use an initial sort into where the particles are in physical space to figure out what's near and what's far, and then that reduces the cost. It is a form of hashing, and that's why I didn't go into too much detail with hashing. So there are three pieces to a bin sort. One is that you have, or in this particular implementation, you have a Boolean valued rectMD array. So all that's saying, so the other thing about this is that not every point in space has particles. So this is really aimed at having a sparse collection of particles. So you have a Boolean valued rectMD array. It's just saying true or false depending on whether that particular region in space has particles. And that's m underscore bitmap. This is something I cut and pasted out of a piece of code I'm working on. So here, the second thing you have is actually a vector of things, of, a vector of particles, for example. So in each, and what this represents is for each point in this bitmap that's true, I'm going to store all the particles for that point. And then the third thing I need is that I have to map between where the points are and an index into here to get to the particles. So that's m underscore, and that's a map of point and int to get patches. So how does this work? So here's a picture. So I've marked as x's. These are points where I actually have something. I have particles in them, let's say. So each one of these boxes contain some number of particles greater than 0. All the places where I don't have x's don't contain particles. So that's my rectMD array Booleans. It's just, do I have something there or not? It's encoding more information than that because the index tells me where I am in space. Because I can figure out from knowing the value of the point corresponding to this point here, where it is I am in physical space. And I can also figure out who my neighbors are, what things are close to me. And I can ask, okay, which of those things am I going to have to talk to if I'm doing things that have force calculations that depend on neighbors? I still need to get everything though. So given I'm a location in space, now I have over here this vector. The vector contains, for each point, it contains the collection of things in that point. So in the case of particles, it's a list of particles at each point in the vector. And here's another application, which was actually where I pulled this from, is that if I were doing hierarchical refinement of the grid, each point here would actually be a fixed-sized rectangular grid, say a 64-cube patch, or a 64 square, this is two-dimensional, patch, where I'm doing a calculation. So I would have, for each location in the vector, a rectMD array. Now, how do I get from one to the other? Well, if I'm starting out up here, going in this direction is easy. For ease of notation, I didn't kind of go farther and say, oh, in addition to that, this is not just a list of particles, it's that plus I could have put a point there to tell me which bin it's in. So I could have made it a pair. So going from this list here to where I am is easy. But let's say, okay, I'm in a bin's worth of particles up here. I know how to get here. Now I need to know who my neighbors are. How do I go back? Well, that's what map is used for. So we have map of point in, and what that does is that for each point, you can find out what index this is. So int k is equal to m get contents of point. So here's my m underscore get contents. I'm saying I'm at this point. What are the contents of it? Well, map stores what the integer, in this case, would be 0. If I'm at this point, get the contents, map would store the integer, and I'd index into get contents with a point and get 1. And in fact, I have this backwards. The key for map is not int. The key for map is point. So I'll be correcting all of these things. So the key, if the key were int, it'd be easy, or relatively easy. But the key for this is point. Now, again, if I were going the other direction, so one of the things I would do is now I'm sitting at this point, and I need to know, okay, what is the location of my neighbor? Well, I know how to go to find my neighbor. I just increment the point by 1 in that direction, for example. And I see Boolean is true or false, so I have particles there if it's true. Where do I have those particles stored? Again, I use map, index with point, to get where it is, where those particles are stored in this vector. So this is a very typical example, a very typical pattern of what you do to sort particles, for what you do for adaptive gridding. Now, one more thing, just as a hint, why would I use map instead of unordered map? I'll give you one reason, or that's kind of exotic, is that why would I want to use unordered map, first of all? Well, if I use an ordered map, I have to define an ordering on points. Well, I can do that, and it not necessarily mean anything. However, one of the things you can do is define orderings on points that approximately preserve locality. So these are so-called space-filling curves, and and what they will do is kind of modulo log n considerations. If you have a point here and you look at a point that's nearby, its location here is going to also be nearby. So the reason that's good is that when you do this in parallel in CS267, you want to cut things up into contiguous chunks. And a good way of doing that is to use space-filling curves. So you'd use an ordering on your points for space-filling curves. Your linear ordering over here would roughly preserve locality, or at least a lot better than would if you did nothing. And then you can send various chunks to various processors. So, to my 3 live audience, any questions on this? So to review, we have 3 containers, and they have overlapping capabilities, but definitely strengths for each. Vector, which looks like dynamic arrays, where you're not having to manage the new, delete, the copies, all the rest of that. All that is taken care of for you. But in terms of how it looks like an array at any given moment. Lists are things that get rid of the weaknesses of arrays, that is, the ability to insert and delete arbitrarily. By the way, you can sort lists as well. You can sort any of these things. It's just a question of how much they cost, how much it costs. But you don't want to use them when you're trying to do random access. And then map, the way to think of map is to think of it as a dictionary, the way you would use a dictionary. And that's the simplest way to kind of keep that straight. It allows keys to be something other than ints. It allows keys to be, which is what a vector is. So it's like a vector in that you can index into it. You can do random access, but you can do random access with more complicated things, provided they're ordered. And if you use unordered map, they don't even have to be ordered. All right, we're done a little bit early, which is not so surprising since we still have another lecture to do. So let's take a break. Okay, let's get started. So I think I'd like to start, before getting into the lecture for today, with a couple of opening up for questions from people from the homework, and also answering a couple that I thought, in case that came up on Piazza, that I thought were worth repeating. So could I have the whiteboard lights? Good. So let me just mention a couple of them. One is the the question of what is the relaxation parameter. So it is mu is equal to h squared over 4 times the dimensionality of the problem. And one of the things that you can do to see how that's a natural one is you look at the error equation. If you look at delta L plus 1 is equal to delta L, and then you say mu L of delta L. That's the equation for the error. And if you use this value, you get delta L so let's do this at ij, just in 2 dimensions, or ij, that's fine. Delta L, for this choice of the parameter, you get, this is 1/2 delta L plus 1/4 in 2 dimensions times this is at ij. Let's not even do it as a sum. Delta I plus 1 j plus delta I minus 1 j plus delta I j plus 1 plus delta I j minus 1. So it is the average to get the new error. It's the average of the old error plus the with the sum of the things at nearest neighbors. In 3 dimensions, it's the same thing. It's 1/2, or qualitatively the same thing, 1/2 delta Lijk plus the sum over neighbors of delta Ijk plus whatever, where neighbors are defined to be, in this case, in 3 dimensions, all 6. So this was chosen quite deliberately, and it is the correct dimension-independent expression, or has the correct dependence on dimensionality, I should say. And in both cases, what you're getting as your error equation is kind of the best you can hope for, given that you're doing point Jacobi, which is that you're taking the error at a point and reducing it by then taking the errors at the neighbors of the points, and the new error is the average of those two. So that's one issue that came up. Second issue, which is kind of a completely different thing, is some discussion of destructors, and some confusion, and I kind of resonated with that because I was confused about destructors for a long time. So the question is, if you have a class T, and you have public, and now you have default constructor, T, and now you have a destructor of T. Now, what has to be, so in the case of constructors, there is a default constructor and it has a default behavior. for a default constructor, the default behavior is to look at all the member data of that object, of that class, and call the default constructors on all of them. Easy enough. There is, for destructors, there's an implied default behavior, but it's not generated for you. It's in some sense not quite generated for you automatically. So default behavior, call all the constructors. Unless you were to do something else. I mean, you can make default constructors do something. But if you don't give it any definition, it will just do the default behavior. Now, in constructors, there is a default behavior. And the default behavior is execute whatever code is in the definition of the destructor. And once you've done all that code, then call the destructors for all the data members. So, the reason why it's not quite symmetric with constructor definition is that you actually have to define what that body is, even if that body is empty. So, you actually have to have a definition, not just a declaration of the destructor. But this also clears up one of the things is, how do I know it's cleaning up after itself? The default behavior, the automatic behavior for constructors is call default constructors for my member data. The default behavior for destructors is is to execute the body of the destructor and then call the destructors for all of the member data. Completely symmetric. So you don't have to worry about it. So for example, rectMD array has a data member mbox. When rectMD array's destructor gets called, yes, you have to delete the m_raw pointer. You have to do a delete on that, otherwise you'll have memory leak. Because mbox, it's just like any other variable when it goes out of scope. You can think of a destructor as ultimately when a destructor is mostly called. They're not called explicitly by you. They're called when a data member, when an object goes out of scope. And what happens when you go out of scope? Well, everything gets cleaned up after itself. Destructors are called for any data when you go out of scope. And this is the mechanism by which that happens. So those are two questions that intrigue me. Are there any other questions that people have that you might want to bring up here? Or that haven't been answered adequately on Piazza? All right. All right, so now I'll go back to the slides. And let's see here. I think after my experience this morning, I will stick with PDFs. So one of the challenges with the arrangement of having two lectures today is to have two lectures that did not have any dependencies on lecture 8, did not depend on lecture 7, and I managed to luck out. So I think we're okay there. So what I'm going to talk about today is kind of the lead up to the next set of patterns, the next set of motifs, and they kind of get strung together: unstructured grids and sparse matrices. Unstructured grids kind of generate for us sparse matrices. So what you're going to get today is a kind of whirlwind tour of finite element methods, among other things. Yeah. So, as I warned you at the beginning of the course, it's Poisson's equation almost all the way down. Not quite in this class, but we do a lot of it for generating examples. To start, let's do a little bit of vector calculus. So when and this is all going to be in 2 dimensions. 3 dimensions it's more work to generate examples. It's substantially more work than it is in 2D. So I'll stick to that notation. Gradient operator is given a scalar function. The gradient operator is the vector whose components are the partial derivatives in each of the coordinate directions. The divergence operator is given a vector-valued function, a vector field, fx with components fx and fy. The divergence is the sum of the partial derivatives of each of the vector fields in the corresponding direction, partial fx, partial x, partial fy, partial y. Given these 2 definitions, you can write Laplacian as the composition of divergence and gradients, the divergence of the gradient operator, and except this should have been phi, not psi. We also have Green's theorem, which is integration by parts, that says that the integral of psi of divergence of anything, but in this particular case the gradient, is equal to the gradient of psi dot the gradient of phi plus the boundary term. So this is the integral over domain omega, integral over domain omega, and this is the integral over the boundary of omega of psi of x times grab psi of x and then dotted into a normal. There's a normal missing here. So the important thing is that if psi is identically equal to 0 on the boundary, this term goes away. And all you have is psi with Laplacian applied to phi is equal to grad psi dotted into grad phi. So this leads us to a different way of formulating Poisson's equation. This is a weak form of Poisson. So if we want to solve Poisson's equation, and note the sign convention here, we're using minus Laplacian of phi equal f. That's kind of the convention in the finite element world for reasons you'll see in a moment, is equal to f on this funny shaped domain, omega, and phi is equal to 0 on the boundary of that funny shaped domain or any other domain. And we want to find a weak solution. So what that means is that the integral of minus Laplacian of phi of x, psi of x dx is equal to that. That's how we derive what the weak solution condition is. For all piecewise smooth test functions, psi of x with psi bound equal to 0 on the boundary. If we apply Green's theorem, and this is the part that makes the solution weak, just formally applying Green's theorem, this becomes grad phi dot grad psi, and that's equal to the integral of f of x psi of x dx for all psi in some set of test functions. So rather than saying Laplacian of phi equal f, or minus Laplacian of phi equal f, we're saying that a somewhat weaker condition. This requires 2 derivatives. This here says that, okay, the gradient of phi dotted into the gradient of some collection, of sufficiently large collection of functions, integrated over your domain, is going to be equal to the integral of f multiplied by the integral of phi integrated over that domain. You only need 1 derivative here, not 2. Ultimately, when you have f be smooth enough, you'll end up with all the derivatives you need. But still, this is a different way of specifying what it means to satisfy Poisson's equation. It's also a more indirect way of specifying it. We're not saying that phi satisfies a differential equation. We're saying that there is this relationship between inner products of the gradient of phi with a whole infinite collection of test functions, and then we have this thing on the right-hand side of that relationship. On the face of it, this sounds like it'd be harder to do because instead of having, in some sense, one equation, you have an infinite number of equations, and you have this test function space in the way. That has to be specified. However, what the advantage of this approach is that it leads to a way of discretizing that has some very nice properties. So this is a finite element discretization, and it comes in a bunch of different pieces. Step one is that we discretize our domain as a union of rectangles. So here's a little cartoon up here. So you have, so here's a domain in space, omega, and the way we've discretized it is we've laid down a bunch of points and connected them by line. So we've represented, there's a representation here as a graph. And one way of thinking of it is that we have a bunch of points in space. But there's really more to it than that, is that they define a collection of triangles whose union covers the whole domain, and exactly covers the whole domain. This is one of the reasons you like this approach, because unlike in our first example, where everything had to be a rectangular patch, this we don't need much in the way of constraints on the geometry. We can find triangulations that cover arbitrarily, contorted and strange-looking regions. So that's the first part of any discretization is in some sense discretizing how you discretize space. And we're discretizing our domain as a union of triangles whose nodes form a graph for which the edges of the triangles are the arcs of the graph. Now we discretize space. Now the next thing we do is we discretize our test function space. We replace V by VH, a finite dimensional space of test functions. For this exercise, we're going to use linear combinations of continuous piecewise linear functions indexed by the interior nodes and linear on each triangle containing a node. So there's a lot of words, but here's a picture. So for each node in the interior, ones that are not on the boundary, we define a test function. It's 1 at that node, it is 0 on all the other nodes, and it's linear on every triangle. So that's enough to uniquely specify a function. It's a function that on the shaded triangles, it's a linear function divided by 1, 0, 0 here on these 5 triangles, and it's 0 everywhere else. That's one test function. We have one test function for every node in the interior. That gives us ni test functions. So it's a finite dimensional set of test functions. Step 3 is that we now have test functions, but we're also going to use this. And it's a basis in the sense that if I had an arbitrary collection of values on the interior nodes, I can always write them as a linear combination of, I can write them as the values of a linear combination of test functions with the, so that that collection of piecewise linear functions interpolate those nodes, those node values. So there's an interpolation property buried in here as well. We also, the final step is how do we approximate the solution? Well, we're going to use the same set of test functions to approximate the solution. It's going to be a linear combination of the elements in VH. Now, so in the back of your mind here, VH is a basis for by definition, for a finite dimensional space. It's a minimal basis in the sense that the dimensionality of the space is ni, the number of functions is ni, so there's no redundant functions here. And we're using that basis to construct solutions, approximate solutions. So we apply the weak form of the equations to the finite dimensional subspace VH. So here's how we go from weak form to a matrix equation. So we approximate, as I said, phi of x is approximated by phi h of x, the finite dimensional approximation, which is just the sum over n sub I over the interior nodes of weights an times basis functions. By the way, some notation back here that I forgot to mention. I will denote by the collection of interior nodes ni, script n sub I, and the elements I will always denote as a kind of linear array going from 0 to e minus 1. So they're E elements. So this is saying we're just going to approximate our function as a linear combination of basis functions. And then what's the condition that this is a weak solution translated into this finite dimensional space? Well, it's grad phi h dotted into grad psi h sub n. So we take this function here and we say for every element in our finite dimensional space, or equivalently every element in the basis for that, then phi h dot grad psi n of h is equal to in the integral over omega of that, is equal to the integral over omega of f times psi hn for every interior node. Writing out definitions, we find, okay, we have a sub n, this is the sum over n prime a sub n prime times this quantity here, grad psi hn prime dot grad psi hn, integrated over omega, and then the integral over omega f, the same thing we had before. This is actually a matrix equation for these expansion coefficients. L of a at n is equal to the sum n prime over ni, L of n prime, a at n prime. That's equal to bn. What's L? We know what a is. A is the expansion coefficients. What are L and b? Well, L is easy. L is just the L of n prime is just the dot product of grad psi h n prime and grad psi h n integrated over omega. Keep in mind, psi h's are piecewise linear. That means in every element, they're a constant vector. Should be easy to do. Bn is the integral of f times psi hn. Well, that's a little harder. These are linear in each element, but it's not so bad. So there are a couple of issues here. One of them is how do we compute L? And the other is what is the quadrature rule we're going to use to compute B, to compute those integrals over F? Because F is, even though the psi's are simple, F is not. F's an arbitrary smooth function or whatever. So let's talk about computing L. Yeah, it's this sum. And how do you organize yourself to compute this sum? Well, here's the trick. The trick is you can convert this sum, or this product, into a sum over elements. And so this is the dot product over all the elements of the integral over an element of grad psi hn dot grad n prime times grad psi hn. All I've done here is I've said omega is broken up into E elements, and they're disjoint. So that means the integral over omega is the integral over each element separately. Now we use the fact that what do these things look like? These look like piecewise linear, or including possibly zero, on psi. On elements. In particular, this is equal to 0 unless n and n prime are both nodes on the same element. So unless let's say this is my nth element, unless the basis function for n prime is one of these three corners of this element, then the contribution to this integral is 0. Just a little bit of geometry. So that allows you to transform the calculation of matrix values into something that is much more manageable. So here's the pseudocode. You initialize L, your matrix, to be 0. You sum over elements. Then for xn prime in KE and nn prime in Ni, L of nn prime is the integral of KE grad Hn prime dot grad Hn. So you're just building up Lnn prime incrementally. And what you've done is, by transforming it to a sum over elements, you're just summing over elements. This is easy to do. If you know you're sitting at element E, little e, then you say, it's easy to do if you are sitting at element E and I know what are the nodes that I am adjacent to and what are the functions associated with that nodes that I'm adjacent to. So what do we know about this process? L is a matrix with mostly 0 entries, because if psi is, if this node is here and you're more than kind of one away, so to speak, like this node here, then there is going to be no element that, there's going to be no element in the support of this node basis function that's going to intersect with the support of this node basis function. But that said, it's a sparse matrix, but it's a nice matrix. It's symmetric. That's something easy to show. And in fact, you can read it off of the original definition. L of nn prime is grad Hn prime grad Hn dotted product. It's the same as if you interchange the order of n and n prime. So it's a symmetric matrix. Turns out it's positive definite. And in a lot of cases, it's an M matrix. I'll tell you what that is in a moment. Now, how hard is this to compute? Well, these are linear on each element. That means grad psi and grad psi of n, grad psi of n prime are constants. They're just vectors. And you can compute the dot product of two vectors and two vectors. But again, the trick here, and it's a bit of magic, and it's special to finite elements, is that we're building up a matrix dimensioned to, that is dimensioned by nodes, by iterating over elements and building it up incrementally. And that's kind of a standard pattern that you have in the finite element world of organizing yourself. You have some sort of substructuring like this, elements, and that allows you to build up matrices that are less structured but have a nice orderly way of building them because of the substructure. Now the next thing you have to do is you have to get a right-hand side. So what's the quadrature for this? Remember, we have to integrate the integral of omega psi hn f is equal to, again, omega is a disjoint union of elements so that we can express these as the integral over elements. And what is this integral? It's the area of, so here's the quadrature rule. The quadrature rule is going to be, we approximate this integral, which is a linear times some arbitrary function, and it's equal to the area of the element times the value of f at the centroid of the element, the center of area, and the value of the basis function at the element, at the center of area. And you can reorganize this in just the same way we reorganize the element calculation. Initialize b equals 0, iterate over elements, and for all xn in this element, and for all n such that n is also an element in interior node, we increment the right-hand side with this value. Centroid, by the way, is defined down here. It's the integral of, it's the area of KE divided by the integral of x dx over KE. So it's the center of area. It's a moment. And again, this has the same kind of flavor of element magic, that is, that started out with something that was sum over nodes, and we've reorganized it into a way where it's a sum over elements that are, and why is that good? Well, if you try to attack this as kind of directly as a sum over nodes problem, here's what you would get into trouble with, is that you really don't have any control over the number of nodes that talk to each other. Here we have one node here, and there are going to be 5 other nodes whose basis functions I'm going to have to talk to. It could be 5, it could be 10, it could be, the numbers could be quite large. But by introducing this level of indirection, everything is sitting at the center of it's element based, and for each element, I'm saying, look at 3 nodes. You build up the matrix incrementally that way, but at any given point in the game, it's look at one element and the 3 nodes adjacent to it, use that to increment a matrix. There's a level of indirection here that limits the, or at least organizes the potential logical complexity. Now, once we have a matrix, what are we going to do with it? Again, the only tool we have in our box at the moment is point Jacobi, which works equally well here. So to solve LA equal B, we compute it as a steady state solution to an ODE. I flipped the sign here, so L is minus Laplacian. It's dA dt minus LA plus B. If all the eigenvalues of L are positive, then L infinity is equal to B, and A infinity is the limit t goes to infinity A of t. So this works equally well for ODEs. Use forward Euler just as we did before, and with some lambda, some time step, pseudo time step. And we stop when we have reduced the residual by enough. All this should be quite familiar to you by now. So what do we know about our matrix? It's symmetric. We've already talked about that. It's positive definite. That's, again, what does that mean? First of all, v dot L of v greater than 0 if v is not equal to 0. This is one of the symmetric positive definite matrices are the nicest matrices you can have. It's not just all the eigenvalues are in the real parts are all one-signed. It's that all the eigenvalues are real positive, non-negative. So it's it doesn't get any better than this when it comes to solving linear systems. It's positive along the diagonal. Rows have to sum to a non-negative number. That's kind of a consistency condition. And if the triangles are sufficiently close to equilateral, the non-zero off-diagonal elements are non-negative, each individually. The sum of them is sums up to a non-negative number, satisfying that inequality. This is the M matrix condition, or at least a big part of it, is that each off-diagonal element is, I'm sorry, this is, I've got my sign slip. All the off-diagonal elements are negative. The rows sum to a negative number that satisfies this inequality. So, but this is the M matrix thing. Is that think of if you think of our original structure grid matrix as matrix, what you had was h squared. You had 4 over h squared on the diagonal, and then you had minus 1 over h squared off the diagonal. So each it was the other way around. It was minus 4 over h squared on the diagonal and 1 over h squared off the diagonal in 2 dimensions. So that says that an M matrix is where the diagonal has one distinguished sign and the off-diagonal elements have the opposite sign, and that there are these inequalities like this that are satisfied. They're the nicest matrices you can do. The fact that this is an M matrix is related to the fact that when I said by choosing the right relaxation parameter, I can guarantee in max norm that the error goes down. It can never go up. It's not that it can't go up in some integral squared norm. It's that in max norm, the error can never increase using point Jacobi. So as I said, the best possible matrix you can get. We still have to choose a relaxation parameter, and we do it much in the same way as we did for the regular structured grid case. Lambda is equal to alpha times 1 over the max over k of the diagonals, where alpha is less than 1. So in the corresponding thing we did for point Jacobi for structured grids, alpha was a half. Now, if your grid is strongly varying, you might want to use a local relaxation parameter. That is, instead of using one single alpha everywhere, you would use a lambda k, a different alpha at every location in k, where lambda k is equal to alpha divided by the local value of the diagonal. You won't be doing this in this assignment. There's a corresponding thing that occurs when you do structured grid calculations, but it's for the case where you're not solving Poisson's equation, but something that has variable coefficients. And in that case, you have things that are analogous to not having the diagonal vary, and using local relaxation parameters sometimes is desirable. So we've managed to formulate everything to get to a point where we can compute we need to solve a matrix equation. We'll use point Jacobi, but we still have one more thing to do before we can proceed, which is actually figure out how we're going to organize ourselves. Again, going back to this picture here, this is not going to give us a matrix that has nice geometric structure. That is, you know how far, you know what your connectivity is. Things are going to be more general. It's going to look more like a general sparse matrix, and we need to do something about that. So let's go back to our sparse matrix pattern. That compact basis functions, which were what you're using, is going to lead to a linear algebra, a linear operator matrix that has mostly zero entries. This is kind of a crazy mostly zero entry matrix. The ones we're going to use are not quite so crazy. But they're still general sparse matrices. So how do we manipulate things? So what do we need to do? We need to be able to store the matrix. We need to do matrix multiplication by a vector. That's what all these operators are. We're going to need to compute L of A. We're going to need to, and that's it. And we're going to obviously need to store L. So how do we do matrix vector multiply on a sparse matrix? How do we organize ourselves to do that? Well, you can always put it in a multidimensional rectangular array as if all the entries were non-zero. You don't want to do that. That's a straw proposal that you take a blowtorch to. You waste huge amounts of memory storing zeros in a lot of places. It's also a huge matrix. It's going to be Ni by Ni. If you think of Ni as being comparable to the number of degrees of freedom you've had on a structured grid, it's in 2 dimensions n squared by n squared, and 3 dimensions n cubed by n cubed. It's a horribly huge problem. You never want to do that. And waste. You don't want to do it. So we'll use sparse matrix representations, and this is I've already discussed this in the first lecture, but this is actually the representation we're going to use and implement. So here's my original little cartoon sparse matrix, mostly zeros and has non-zeros. How do I represent that? Well, the representation we're going to use is the so-called CSR, compressed sparse row representation. And here's the representation. We represent a sparse matrix as 2 vectors of vectors. So one of them holds the matrix elements, and the other holds the column indices. So how does that work? So here is my vector. So this is an 8 by 8 matrix. Both of my vectors are going to be of length 8, the length of the size of the matrix, the number of rows. And for each row, I'm going to store another vector. And it really, in this case, is going to be a vector because it can have different numbers of entries depending on the row. First row, I have just one non-zero entry. I store that one non-zero entry in the vector of doubles. It's a vector of length 1. what I'm storing here is what column is that in? It's in column 1. Next row, so in the next vector of the next element of my vector of vectors, I have a vector of length 2 for the column entry, so I have a non-zero at 2 and a non-zero at 4, and then I store the values here, 2.3, 1.4, and I keep going. I did one thing down here to emphasize something about this, is that down here at row 7, I'd stored 7 and 3 and the corresponding values 4.9 and 1.9. Notice that this ordering here doesn't have to be the order in which the matrix elements appear. The 7th element, 4.9, appears in this vector before the 3rd element, 1.9. That's perfectly okay because we're storing these column indices. And when it comes time to do matrix multiplication, this will give us enough information to do the right thing. So here's what your sparse matrix class will look like. Part of your second homework assignment will be to implement this class. So you're going to set up you implement it for general m rows and n column sparse matrix. So the constructor is going to look like, takes the number of rows and the number of columns. And what is it going to have to do? It's going to do matrix vector multiply. That is, if you have a input, you have it's an operator, star, that you take a matrix star a vector of the correct length of size a sub n, returns a vector of size of length a sub of m. So that's this operator here. And then the things that allow you to get and set operations of matrix elements is an ordinary indexing operation. You have a pair of integers, ij. You can index with a pair of integers ij and get back a reference to the double. Now, there's some magic you're going to put into this. If necessary, the sparse matrix class is going to add a new matrix element when you reference that location and initialize it to 0. Now so these are the public interface, the functions that you're going to be able to call. Here's what the internal representation we're going to impose on this. We're going to have, what are the dimensions, mn, mn. It's convenient, and this should be a double, not a float. It's convenient to have something called a 0 hanging around, and as a return reference value. You'll see when we go into more detail on this why. Now here are the two classes that we talked about here. Vector, vector of double. They're the two objects. We have a vector, vector of double that holds the values, and a vector, vector event that holds the row indices. So this is enough. This interface, I claim, is enough with an appropriate set of finite element tools to build up the matrix starting from a finite element description of your discretization. So what's the setup for homework 2 going to look like? We're going to build an operator corresponding to a triangular element discretization of Poisson equation. We'll use an iterative operator solver to solve this equation. What are we going to provide? What's going to be given to you? We're going to give you triangular grids that are stored in files, and classes for reading those files and storing and manipulating and computing geometric information. And then a class for writing out the solution in a form that can be viewed by visit. So in some ways, more of the kinds of framework that you got in the first assignment. Except you're going to be asked to do more here. What you're going to write is a class FE Poisson operator that generates and stores the sparse matrix and applies the operator to the right-hand side. And then the second thing is a sparse matrix class. You're going to have to implement sparse matrix. And then the third thing is an implementation of point Jacobi to solve the resulting linear system. Now, item 3 should be easy. If I give you matrix vector multiply and you have the rest of this stuff, it should be a couple of lines to say, you know, your code for doing this should look not a great deal more complicated than this mathematical specification. So that's what we're going to do. And now I'm going to dive in and tell you what things we're going to provide to you. The things that we start out providing with to you is kind of the setup for defining finite elements, triangular finite elements in 2 dimensions. So you have to have, and the way we do this, we have a class for node, we have a class for a single element, and then we have a class that kind of puts them together into a finite element grid. So here's the class for a node. It has a default constructor. It has a constructor that is an array of takes an array of double dims that should be a reference, a underscore position. It also gets assigned an interior node ID and a Boolean that asks the question, am I an interior node? So one of the things that's important here, going back to our calculations, is that everything we're doing is all keyed off of interior nodes. But for the purpose of displaying solutions and things like that, you sometimes want to have all the nodes. So, and in fact, for defining the elements, you have to have all the nodes, because it takes 3 nodes to define an element, even if 1 or 2 of them are on the boundary. So we have to distinguish. Let's go back to node. One thing that I'm doing here is, last time I taught this, I was still not quite certain that array was completely robust, and that was probably too conservative on my part. So I was using consistently either C arrays, or since C arrays can't be passed as return values, vectors. Now I'm embracing arrays, and one of the things I'm going to have to do this weekend is rerun the code for this assignment and make sure that I do not get paid for my courage and my convictions. So now we're using array here. So you're going to see little things that are mistakes. For example, when I started retyping these, I forgot to put in a reference because when we had this as a C array, you didn't have a reference. We can get the position of an array. We can get or of a node. Nodes are points in space, so it makes sense to talk about their position in space. You can also get the interior node ID if it is an interior node, and you can ask the question: is this an interior node? And then the private data is an array of doubles, which is the position, a Boolean which says, am I an interior, and an integer that says, who am I? There are different integer IDs for nodes. One of them is, where are they in the vector of all nodes making up the triangular grid? Where are they in the vector making up the interior nodes? And where are they in a vector making up the nodes on an element? You'll see that one in a minute. This one is not part of the data representation of node. That's part of element. And here we are at element. So what's an element? Public interface, it's a class. I'm defining vertices up here. By the way, this is another small piece of programming standard. Even though this entire assignment is being done in 2 dimensions, I am still using a macro dim. Why is that? It's a documentation issue. I want to know which appearances of 2 as a literal are dimensionality, and which appearances of 2 as a literal are the fact that matrices are doubly indexed by integers. So all the places where dim2 is the dimensionality, I use dim and make the macro and make the C++, the C preprocessor turn that into 2. Similarly here, I define vertices to be 3, even though I know that I'm only going to be in 2 dimensions, which means all triangles have 3 vertices, whereas if I were in 3 dimensions, the number of vertices in a d-dimensional space for tetrahedra is the dimensionality plus 1. But I still use that because I want to make sure I can see what I'm doing. So this has a name in old-style software engineering, which is no magic numbers. You don't want to have kind of integer literals sitting there if you can at all avoid it. You want to have them have names that express what their function is. So public, we have default constructor. We have a element, which is a constructor, which is an array of ints of size vertices. And I'll tell you what those are storing in a moment. And then you have a destructor. All these are storing is the indexing to get the node number. These 3 integers, so you have an element is defined by 0, 1, and 2. There are 3 nodes there. All you need to know is how do I access the nodes? And from the nodes, I can get the position of the vertices of the triangles. I can get everything else. So all I need to store in my elements is where do I get my adjacent nodes? Now we move on to FE grid. Public interface is going to be a default constructor, a constructor that reads from a file. At this point, again, I'm going to go full metal C++ 11 and get rid of all this char star stuff and call them strings. And then a destructor. You have to be able to get the number of elements, nodes, and interior nodes. How many nodes do you have? How many elements do I have? How many nodes do I have? How many interior nodes do I have? In addition to that, you need to have things that allow you to do calculus. And again, we're going to kind of element-centered calculus. We're going to provide them to you. Compute the basis function at a node. So for any interior node, get the, these are the things you need. You need to know what your local node number is on an element. So, so this is, in order to, and when you do that, then the gradient on an element is going to be given an element number and given the local node number, compute the gradient for the basis function corresponding to that node, for that node on that element. Another thing you can do is compute the centroid on an element. Well, that's a number that's independent of which node you're looking at, which basis function you're looking at. So that just requires you to look at an element number. Compute the area of an element. That's just an element thing. So that we're building up all the things that we were talking about before, the things that you need to do in order to compute do the finite element calculation. Element area to compute the gradient, which is relative to a basis, to a particular basis function. Compute the centroid and the element area, which are intrinsic to elements. Those are just geometric quantities. And then compute the element value, which is the which returns a number. This one I have completely forgot. I did not look at this particular one this morning. So let me see if I can parse it. It's taking a position, it's taking a gradient, it's, all right, I'm going to defer that because I clearly have no idea. So what else? How do we get a node? We need to have an element and a local node number. By the way, what are these local node numbers? It's an arbitrary assignment, 0, 1, and 2. And that's because you're iterating through nodes on an element, so you have to iterate through three of them. And then you get a reference to a node given its global index. Given a node number, given a node number, I can get back a node. What's underneath the hood in all of this? What's underneath the hood in all of this is a vector of nodes, a vector of elements, and how many interior nodes. That's all that we're storing in FE grid. So notice what we don't have. We don't have either an explicit mapping that gives all of the elements touching a given node, nor do we have a mapping that maps interior nodes into nodes. The first one we don't need, because what we're going to do, we're never going to try to do anything that's node-centered. Everything is going to be mediated through build up incrementally from summing over elements. So we never need to have, oh, let's look at all the elements touching a node. And then the second one we don't need because we've already implicitly encoded it in node. We know what nodes are interior nodes. Now, this is what you will be implementing. FE Poisson operator has a default constructor, has a constructor that sets its FE grid. It knows how to apply the operator, and I use kind of the notational conventions from before. Here's the right-hand side. Here's what, when I want to apply the operator, here's the output, here's the input. It doesn't change FE Poisson operator to apply an operator to something. Make right-hand side, if I give it the right information, right-hand side at nodes, right-hand side at centroids, it does it. You can get the FE grid. I've stored it somewhere. I can get it back again. And I can also get the sparse matrix if I need it. And what are the data members? Well, it's FE grid, which is the thing we've already packaged up for you. And then it's the sparse matrix class, which you will have written. But that's all you have. All of the dynamic variables, AFI, right-hand side, LFI, all of this stuff at right-hand side at nodes, these are all going to be defined on the interior nodes only. So there's not going to be any, not going to be anything corresponding to ghost values. This is doing the thing that's analogous to what we did in the first assignment, where the operator applied to phi was defined just on a set grown by, shrunk by 1. And this is the analogous thing for unstructured. So the game here, once you have all of this that we've given you, what are you going to have to do? You're going to have to build up your sparse matrix. You need to know how big it is. You have a function for that, get number of interior nodes. You need to compute the inner product on each element. You need the gradient and the element area. To fill up incrementally, you need to, again, for each element, walk through the nodes that it's adjacent to, and then incrementally fill in ln. So this is get node, and what interior node ID. What is the absolute location of these abstract nodes in our vector? And then this is just a reprise of the mathematics that you'll be doing. One important comment here is sparse matrix is going to be designed in a way that it automatically adds a new matrix element when you index into that location and initialize it to 0. So you're not going to constantly be saying, does this exist yet? As soon as you try to, use sparse matrix of ij as the left-hand side, it says, do I have it? Fine, I can do that. If I don't, I'll make a new one and initialize it to 0. Building the right-hand side, what are the pieces that go into that? Right-hand side is an ni-dimensional vector. Get num interior nodes is what you need to do that. While our input f is a vector of values evaluated at centroids of elements. So in order to construct that from some continuous function, you'll have to be able to get the centroids. And again, you fill these things in incrementally using the same techniques as before. And I think that's all I have for today. Do you have any questions? Yes?
What's our domain? I know it doesn't matter since you're giving us the triangulation, but I'm just curious.
We have these things laying around. So right now it's just a goofy odd shape. Let me see if I can find it. Okay. So you get a couple of them. I'll show you the larger one. So these are not going to be very big problems because we're not doing anything fancy for the linear system. So this is so it's a little, irregular domain, piecewise linear boundaries, and this is going to be the finer of the two grids. And this is actually a plot of what the solution looks like. So this is what visit will provide. So as I said, not a huge number of nodes. Not a particularly complicated domain, but enough to be able to make the distinction between what you can do on this and what you can do on a structured grid.
And also, how do you define triangulation?
Get someone else's software. The gold standard for a long time, and I still think it is Jonathan Shuchuk's for 2D, is Jonathan Shuchuk's triangulation package, which is a very carefully done piece of mathematical software for doing triangular grids in 2 dimensions. So there are various conditions that you want to be satisfied in order to get the nicest matrices possible, and he's able to get those to be satisfied. But there are other kind of more general packages out there. There are 3D things. In truth, the problem, now I will reveal my own prejudices on the subject. I do not use unstructured grids. I am an amateur at this. This is my being. This is one of the patterns, and we need to learn about it. One of the major problems with unstructured grids is that the way that grid generation interacts with the niceness of the linear systems is still tricky, is still not a completely solved problem. So that's, there's, as I said, there's still art out there in doing grid generation in this space. If you're interested in following up, I can ask my friends who are better at this and more invested in this what their grid generation package of choices. Other questions? Yes.
Kind of as a follow-up to that. So with the grid generation, like the quality of it, would it come into play on relaxation factor?
Absolutely. Well, indirectly, I should say. The choice of relaxation parameter for point Jacobi is just the diagonal, and how exactly the diagonal interacts with the grid generation is a little bit tricky. It's a question of, I think the place where it comes in most is to what extent can you rely on this being an M matrix? And that makes the iterative scheme more or less robust. So what other things can I say about that? No, that's I think that's the answer. It's also the case that you don't want to use point Jacobi, right? You want to use something better, some sort of conjugate gradient method. And there, yeah, it will interact with the mesh quality. Other questions? All right. I've been talking more or less since 9:50, so I think I'm ready to call it a day today. There will be office hours, 3 to 4:30, 727 Soda. I'll leave the mic on because, yes, we have extended the deadline for the homework till 11:59 on Thursday evening. Please come and talk to me if you're stuck. So that's why we have the office hours. All right. And also Piazza. I like Piazza because then everyone gets to see what happened.